Hello, good morning, good afternoon, good evening, everyone. This is Vance Hilderman and Jeff Stevenson from AFuzion in USA. And my goodness, the number of people coming to our bi-monthly training technical webinars is huge. Looks like probably the majority were not able to log in because it's limited to 1,000 registrants. Sorry about that. We'll, if you registered and can't get in, I guess you're not listening to this now, but we'll send you a copy of the video link. So today's technical training webinar is, the 10th or 11th in our ongoing series. This one is about winning military aviation contracts by using ARP4754, 4761, DO-178C, and DO-254. It's interesting because the military originally was not on board with DO-178, then 254, and certainly not 4754-61. But recently, there has been an explosion in military entities using the ecosystem of civil aviation. So our agenda for this 1-hour training is to give you a brief condensation of what we train many of our clients. I think we have 15 or 17 ongoing military clients, several hundred in our history. And we want to show you what the differences are with civil aviation versus military, and then move on to military compliance, unique attributes, military versus civil, and then cost factors. At the end, we're going to have time to ensure that we have Q&A for you. So with that, let's begin. And again, this is a subset of training that we provided to, I think 21,000 engineers at most avionics companies and aviation companies worldwide. With that, let's have a quiz. You know how this works. True or false? And we'll give the answers in 45 minutes at the end of this. So, traditional legacy military system standards emphasize safety. True or false? A legacy similarity between military and civil aviation was white box testing. And folks, black box is where you don't see the design software logic. White box is where you do. You actually look at the software in addition to black box. Number 3, guidelines such as ARP4754A, and it is not called ARP. Please don't call it ARP. It's ARP from SAE. ARP4754A, 4761 are not commonly applied to military. True or false? Number 4, oh goodness, we get this one all the time. PDR, that's preliminary design review. CDR, critical design review, is almost identical to stage of involvement number 2. True or false? And number 5, applying ARP4754A, 4761, DO-178C, and DO-254 to military projects should increase the cost by 150 to 200% over traditional military compliance costs. Interestingly, many customers believe it's even more. What is the real answer for 1 through 5? We'll give those answers in 45-50 minutes. So with that, let's dive in. A quick background on AFuzion and your presenter myself here. AFuzion is one of the world's largest in the world aviation certification, training, mentoring, consulting company. We have engineers on-site, off-site in 20 countries. You hear that siren in the background? That's what happens when they don't have good standards. I think the police go after them, right? Well, make sure the police don't go after you. I'm broadcasting from AFuzion's offices in downtown Los Angeles today. We're keeping it safe here. We also have proprietary processes, checklists, templates, training, consulting in 4754-61. That's the system software ecosystem for safety. Then 178C for software. 254, also airborne hardware. 278, ground-based systems, including UAV controllers. DO-200, which is the aviation data. We've worked for 90% of the world's top 100 aviation development companies. If you are flying in an airplane, missile, fighter jet, cargo jet, probably our software, services, hardware is in there somewhere. I'm the CEO of Aviation. I was a founder of 3 of the world's largest avionics and aviation development services companies, and I've personally trained over 19,500 people, which we believe is about 2.5 times more than all the other instructors in the world combined. We've done a lot of work, and you don't want to hear any more about that, so let's go. Military compliance. What's it really all about? Well, let's take a look at some examples of military aircraft. C-130, C-17, B-1, B-2. Those aircraft had many new and reverse engineered avionics systems following a prior DO-178B. F-35, fighter jet. Very good, all things to all people aircraft. Most of the avionics systems, via Lockheed's insistence, are DO-178 compliant or an equivalent. And then the recent KC-146, the Boeing refueler. Civil airframe, based on a Boeing. Military equipment, mission equipment, it's 178 compliant. But are they really? What are the differences? There's some very, very interesting issues that we have to consider for military that simply don't apply to civil. For example, we have functionality in the military for which there is no regulatory basis. Civil aircraft don't have these functions. Now remember, when the military first started with DO-178 back in the late 90s, it was not to increase aircraft safety, crew safety. They had a different purpose. They admired the way Boeing, Airbus, civil aviation developers were achieving cost-effective reuse, cost-effective, more on schedule. That was back in the days. Tongue-in-cheek deliveries of their aircraft. They had an ability to reuse commercial components. The military originally wanted a different version, a military type standard, kind of like we had the language, the software language, ADA, or as my friends in Europe say, ADA, ADA. That was largely a military aviation-based language that was used also in the commercial world. The challenge with ADA, and it's a very good language. I'm an old ADA instructor, both literally and figuratively. But ADA is a terrific language, very safe. The problem is tools, updates, modern, cost. And where do you find ADA compilers and people that aren't at least 25 years old? Okay, so military instead converged on the civil standard and said, let's use the same exact civil standard starting with DO-178, and that was DO-178B. So then we'll be in common. But look at these. These are issues that don't apply to the military realm. Search and rescue, dedicated communication radios. We don't have that in the civil sector. Coupled flight, formation flying. In general, we try to stay away from formation flying. I remember when I was getting my pilot license for ground school, oh boy, we had to keep at least 500 feet. That's 150 meters for you other folks, non-Americans, away from anything. Not in the military. With coupled flight, we have dedicated communications radios. There's auto flight customizations, aerial refueling, KC-146. Seems simple, it's absolutely not. The boom control, fuel management, very complex software. The pilot of the boom, and it is a pilot on board the refueling aircraft such as KC-146, are literally flying the boom. Imagine if they miss. Weapons delivery. Now weapons are interesting. The weapon software and hardware themselves are largely not certified. It's the launch sequence. All public information, folks. You can Google that. So go ahead, check the Google. It's the launch sequence to get that missile a safe distance. Then terrain following. Now I've worked on traffic collision air avoidance systems, TCAS, and there we want to avoid ground terrain following, if you know what I mean. We avoid low-level operations, anything under 500 or 1,000 feet, but not in the military. We like it down there. Black, silent communications navigation is very important. High-performance operations, military mission software. Now, there's some key differences with military. So since the military, starting with the US, and as we'll see, growing to the rest of the world, the military wanted to have a unique application of the standards, but they realized the folly, the mistake of adopting a different standard or changing it. But nonetheless, there's some different interpretations. For example, what we'll see here in the next few minutes is less but different emphasis on safety analysis. Remember the old 882 standard for aviation safety in the military realm. Very good standard, but rather subjective on some of the criteria, and a little bit like mixing oil and water with the civil standards. So the military had more of a focus on mission success probability. Remember, the purpose of a military aircraft is not to avoid getting shot down, but instead to engage, perform its mission, and achieve it. So using these standards for civil world is also applied to mission success probability, not necessarily only pilot and crew safety. So that means there's less redundancy. There's also, imagine, helicopter, weight, power, fighter jet, limited fire control, power, and space. Redundancy is weight. Imagine having 3 of everything. Well, level A, as we call it, we have less room and power, but we do have a harsher operational environment. So the question is always, does the civil sector measure up? Next, there's many onboard mission systems. Imagine anti-submarine warfare, flight planning, cargo refueling, setting waypoints, drop points for cargo or missiles. So these provide less direct flight safety impact. We don't change the flight safety systems on board the aircraft. However, the pilot doesn't necessarily use them automatically, so they have a lower criticality, but they're very important. The military wants at least, as we'll see, a level D as in David on these onboard mission systems. They're important for mission success. And typically, there's not a federal government in charge, not a civil, not the FAA, not EASA, not Transport Canada CAAC. It's a military agency approval. So that is different if it's a refueling aircraft built on a civil platform. Then the FAA or EASA would be somewhat involved. And then finally, on a military project, they're paying for the documents. They want them all. On civil, we have a focus, especially with level of involvement over in Europe, overarching properties in the USA, and that might be changing with some of the recent airplane crashes we've all heard in the news. There might be a greater civil regulatory involvement than there was, but traditionally for civil legacy, the FAA, EASA, they focused on auditing the CVEs, the DERs, and if you don't know what those are, you'll want to download some of our free white papers. But the military says, no, we're paying for all these documents. We want to look at requirements, design, code in detail. They'll take possession, they'll review, they own the IP, and can reuse it. Now, if you've been to any of our trainings, perhaps you've seen this before. The question is, how is this different in the military realm? Well, this is identical, and this is what the military is gradually, and today in 2019, almost universally fully adopting. This we call the horse. In the upper left is the head of the horse. That's the safety assessment process. That's based on SAE ARP4754A, the new version coming out this year. If we don't have that, you're not applying that yet, it's 4761. The goal of the safety assessment is to first perform an FHA, functional hazard assessment, and determine what is the development assurance level, also known as the DAL, development assurance level, proper word. It used to be called the design assurance level. Many people call it the level, the criticality level. Criticality, it's all the same. Then, how much redundancy? How much health monitoring? What is the architecture? And that determines then the safety and the system requirements. Then we follow ARP4754A for system development, system planning, system requirements, including safety. Then we deploy software to DO-178C, which are the legs of the horse, hardware, DO-254, It's a continual feedback. Notice that 254 is being changed. If you didn't catch our previous webinar, you'll want to catch the link on that and look at DO-254 for hardware, airborne hardware, and see how that's changed and evolved, especially this year in 2019. We have AMC 2152A. You can get a copy of that on the EASA website. The FAA took it down. The comment period is over and the comments are being incorporated. We expect that to be released in 2 or 3 months, which means 6 or 8 months. Things take time in the aviation world. Now there was a key change. Look at this. See those red lines? That's right. Look at that. Those red lines are the continuous feedback process between safety, systems, software, hardware. In the old days, we simply passed in a staged waterfall method those activities. Not today. We have to show, even in military, and this is a large gap on many of the military projects we do about 20 or 25 gap analysis per year, and they're about 60% military, 40% civil at AFuzion. The majority of those military gap analysis find key gaps, especially in the feedback process, the application of safety systems, proving that we have continuous involvement of derived requirements, safety engineering in the hardware software realm. Now, we have some special terminology. We need to be very cognizant of this for military projects. Certified is what we do for an aircraft or system within that aircraft on a civil basis. So the aircraft is certified, the system is certified, and if you don't know what TSO, Technical Standard Order, TC, Type Certificate, STC, Supplemental Type Certificate, PMA, Parts Manufacturing Approval, if you don't know what those are, check out one of our other webinars or download some of our free white papers. So the components are not certified. There can also be different certification levels. Remember, DALs, Development Assurance Level, within a system and certainly an aircraft. Now, certifiable is for a device or component within a system that's achieving its highest certification, but it hasn't been integrated into the system. It's only when we integrate it in the system that we know it's actually certifiable. Compliant is us today, folks. Military projects typically are not certified or certifiable. They are compliant. So that's certification by an entity other than the FAA-EASA. Now, qualified is altogether different. It's for items which don't fly, but for which the output is not otherwise verified. Qualified is formal approval, for example, of a tool, which since it doesn't fly, it doesn't require certification. Now, for military projects, here on slide 12, we have to show that the planning process occurs first. And unlike traditional military projects where the planning was black box, what does this box, this aircraft do without looking inside? The civil sector has plans that include white box. What is the design, the data flow, the control flow, the decision coverage, statement coverage, modified condition decision coverage, and then integral processes. They're continuous throughout. So the way we show this picture is first comes planning, second development, then in the background is continuous integral processes. The planning process is red because truly it's the most important. Development, warning, danger. But the third process, the integral process, is larger than the other. Integral processes, configuration management, quality assurance, verification, validation, certification liaison. We draw that green because we're an American-based company, even though we have offices in many countries here at AFuzion. But as an American company, we all know the color of American money is green. Green. So the integral processes are expensive, and in fact, over time, they're the most expensive, especially on military. So what is the optimal military aviation engineering strategy? This is our opinion. My opinion, the FAA-EASA does not approve because they don't approve of a recipe, a strategy. It's the end game. But we believe at AFuzion this is the optimal approach. Upper left, we have the safety assessment. That's 4761. We start quality assurance. Then we develop the black box systems requirements according to the plans and standards specified by the guideline ARP4754A. Remember the body of the horse? Then we develop the 5 plans, the standards. Software has 3 standards, hardware has 5, and then checklists for everything the engineer, the aviation engineer does. We then develop traceability, showing bidirectional trace between safety, systems, and the flow down to hardware software requirements. Then we have our first stage of involvement, SOI number 1. This is not an SSR. In a few minutes, we're going to show the difference between the military progress reviews, SSR, system spec review, CDR, PDR, TRR. These are different. After SOI 1, we start development, and that's the bottom half going right to left. We start with high-level requirements, then low-level requirements, then design. Notice the overlap. Low-level are decomposed and derived high-level requirements, but the design is documented but not tested. That's right, we don't test the design. If we test it, it's a requirement. Then we develop the code and logic following the plans and standards based on the design level requirements at high level, and then we perform V&V. Software does not have validation, hardware does. Software cannot be validated by itself. Hardware in the system can. So remember, verification. Does the implementation meet requirements? Validation. Do we have the right requirements? Correct, complete, unambiguous, feasible. So validation is done at the hardware in the system. SOI 3 assesses the completeness of verification validation. It's not the TRR that military has. Then we have conformity review for changes, SOI 4, and then we achieve certification, flight testing. Now, these key plans, they look the same for military, they're named the same, but they have some different content. All of those issues and challenges that we talked about 10 minutes ago need to be dealt with within these plans. So, PSAC, Plan for Software Aspect of Certification. We're going to talk about the nature of the system. For military, we're going to describe what kind of safety assessment was done. Is it mission software or hardware? Is there a legacy basis? Can we use service history? Much more popular, prevalent on military aircraft. In the civil world, commercial aviation, we rarely have the opportunity for software to use service history when it's airborne. We do on the ground, for example, UAV controllers, and we're going to talk about UAVs. But we use CAST, Certification Authority Software Team. We use CAST number 1, written in the late 90s for software service history, and it's really applicable to military. Then we have the quality assurance. Now, quality assurance is really different. On traditional military projects, QA performs the testings. They do and participate in dry runs. They attend every review. But QA is different here on military for civil. Using 178-254, QA approves the plans and standards, assesses engineers' adherence to the plans and standards, and then keeps records of that. Configuration management, this is the same as military. There's really no difference here. Basically, do you have all the processes, artifacts, all identified so that different people, 30 years, and it's not 29, it's 30 years later, can rebuild that software. The software development plan, very different for military versus the traditional military. Software development isn't how we develop code, and the hardware, of course, has a hardware development plan. System has a system development plan. But the development plan talks about requirements, bidirectional traceability, decomposing those requirements from high to low, or in the case of hardware, conceptual design to detail design. Detail design comprises the HDL, hardware design language, VHDL, Verilog, and also then the design attributes, how we design that software. The coding's almost ancillary. Then the verification plan for software, or V&V plan for hardware. Then the requisite standards. Now, there's keys to planning. the plans really must precede development. On many military projects, the plans were tweaked or massaged, changed during development. We don't do that here. We instead, in the 178-254 realm, we document the changes in the accomplishment summary, but the plans must address every aspect of 178-254, 4754A, and 4761. The idea is after the plans are approved by QA at SOI 1 with the cert authority, the military, we never have to open 178-254, 5461 again, because the information as it applies to our military project is in those plans. But we have to provide proof the plans are followed. Now, the military had a loose, liberal requirement for checklists at a high level. Many companies have a large gap on their military projects. The traditional military checklists were kind of light. So here we need detailed checklists, and AFuzion provides those, of course. Jeff can give you more information on that. But we have to provide proof that the plans are followed, and that is done independently when people can be injured or die. So we have to provide proof those plans are followed. That proof is the checklist. Then the plans address what we do, when we do it, and who does it, with just a little bit of how. These plans, again, are typically approved by quality assurance or a compliance verification engineer in Europe or a designated engineering representative in the USA. Now, we begin with 4754. This is different than the traditional military projects. Military projects did not use 4754A 6 or 7 years ago, but in the last 3 or 4 years, starting in the USA, but now in Europe through European document ED 79A, we apply 4754A on military projects. Today at AFuzion, we see about 70 to 80% of our projects requiring 4754A. If your project doesn't require it, you should still look at 4754A on a military project. It's almost a certainty that it will in the future. It's this typical waterfall. Look at this. Planning. 4754A talks about how we have to plan for the safety assessment, determine the development assurance level, criticality level, A, B, C, D, E, determine the system level requirements, including safety, validate those requirements, assess, are they complete, feasible, correct. Then configuration management, process assurance. Now, process assurance is quality assurance with extra vitamins. So remember, QA has 3 roles that we talked about. Process assurance has 2 more, auditing the suppliers and ensuring the ability to manufacture. Production transition, we call it. Then certification. But then we have a concept at the bottom, far left of the aircraft. We have the aircraft function development. We allocate aircraft functions to systems, and we develop a system architecture. We then allocate those system requirements to individual devices, items, software, hardware, and implement, validate, and verify. That's our 4754A development process model. Now, the development assurance levels. This is different for traditional military. Traditionally, in the past, the military used 1 or 2 lower levels of equivalent civil. But what we have per 4754A 4761 is the functional hazard assessment. It says if a single point or likely multi-point combination of failures could be catastrophic, meaning potential loss of aircraft and all the lives on it, complete mission failure, it's a level A. That's the FDAL, the Functional Development Assurance Level assignment. And then if it's hazardous severe, that means big pilot impact, crew workload impact, possibly dead occupants, it's level B. Major is injured occupants, increase in workload. Level D is minor. And of course, level A is 10 to the minus 9th, B to the minus 7th, C to the minus 5th, and go from there. So the key is to determine the development assurance level. Now, this is where the military on slide 18, and we've got just another 15 minutes, so we'll have time for questions and answers, and then give you the answers to that quiz. We start with detailed planning. We have the 5 criticality levels, A, B, C, D, E. we have to show consistency and determinism. But on military, that consistency and determinism now applies to the white box, including software design, data flow, control flow, the determinism, the structural coverage. We have to have traceability top to bottom. Military always had that. Now remember, 178, back in 1980, the first version of 178, and DO-254 was largely transposed with some key differences from DO-178B in the mid-90s, but the military system always had traceability top to bottom. But here, 178, 254, they require bottom to top traceability, showing that all the logic code is there for a reason. We have engineering independence. Now the military was big on IV&V, independent verification validation, where it was truly independent, a completely different organization, perhaps in a different location. The problem with that is different organizations, different locations make assumptions. They don't know the development. So 178, 254, 4754, we like independence, but we like it when it's the same company. Okay, so just different people. So for us, independence means a different person following a different independent process. Now, path testing. This was new to military, showing that all the code was covered, the logic based on if people could be injured, die, or the airplane crash. Tool qualification, up to 20 artifact types, and there are 71 objectives in DO-178C, less in 254 because 254 hardware is very different. There's many different types of hardware, so we don't have the detailed objectives, but there's more the framework. Finally, number 9, guilty until proven innocent. In all of your countries, and it looks like with all the attendees listening in today, looks like over 40 or 45 different countries around the world, you have 1,000 people that were able to log in. Your laws say we're innocent until proven guilty. But here, in 178, 254, 4754 land, we are guilty until proven innocent. It's incumbent, required of us to prove we're innocent by showing that we followed these processes. Now, ARP4754, it is not the MIL standard 882, so that it looks similar enough that a big gap we find when we analyze gaps on military projects is simply assuming that 4754-61 are the same and equivalent to 882. They're not. The 6 basic steps of 4754A are to, first, plan your aircraft's development lifecycle ecosystem, typically using a V model. If you don't know what that is, you'll want to Google Wikipedia that. And then implement safety activities following 4761A. Have the FHA determine the criticality level. Then the preliminary system safety assessment or aircraft assessment at the aircraft level. And that says, what is the architecture? How much redundancy? What are the interfaces? How much health monitoring do I need? And then a bottom-up FAAFASA, where we calculate MTBF of components at the system safety assessment level. We have to define and justify those levels. Now, the military, UAVs, aircraft, they are gradually adopting the civil development assurance levels. Today, they're almost the same, and this is a huge change for you UAV developers scanning the company names, participating, listening in. It looks like about 20 or 30% of you that I know are building unmanned aircraft. So the development assurance level, we've got good news and bad news. The good news, they're going to be safer. The bad news, they're going to be safer and more expensive, okay? Because the UAV development assurance levels are gradually replicating, especially for you large UAVs, you Global Hawk Predators, equivalents, IAI, Elbit, you're at a higher level today. So then define system architecture requirements, then validate those requirements. Perform V&V, CM, but V&V at the white box level. Finally, implement process assurance and prove transition criteria, proving that your gates, your entry exits are all recorded and according to your plans. Now, military criticality level, this is different than civil, even though we use civil standards. I'd like you to think about this. Is the criticality level, like the civil sector for military, is it based solely or primarily upon passenger safety? Aircraft safety, civilian areas. What about aircraft protection? What about circumsystems, where we have many helicopters with built-in anti-missile defense or flares on fighter cargo aircraft? What about mission success probability? Interesting. Now, what we'll see is all of those are important considerations, but the latter, mission success probability, is really a key driver. So, on military projects, we have some differences, things we have to do. These are common gaps Aviation finds when we do gap analyses. So, look at this. We need to first ensure what our compliance baseline is. Do we have applicable technical standard orders for our military devices? And in many cases we do. Not for the military equipment, but for the civil equivalents. TSOs, technical standard orders. Remember, 4754, DO-254, 178, they are generic fitness manuals for systems and aircraft. They don't have specifics for landing gear, flight displays, radar, communications. Those specific requirements are in the TSOs, which provide MOPs, minimum operational performance requirements, not maximum, those are the minimum. And then advisory circulars, particularly FAA, but now EASA with AMC 25152A. Which ones apply? We have to define for military how we're going to apply 4761 or the new forthcoming 61A. It's our opinion at Aviation that the new version of 4761, and it is done now, the new version is called A, 4761A. It will be required for most worldwide military systems. Real departure from the 4761 we have currently today, which is optional typically. And then DO-254, almost exclusively going to be applied to hardware, but military systems have legacy hardware, and again, through CAST 1, Certification Authority software team, but it includes hardware, a application of service history, legacy compliance, and then ground-based software and systems, very prevalent in the military. We're increasingly seeing the application of DO-278 to the military. If you'd like more information on that, you can download one of our free white papers at the Aviation website on DO-278. For example, a UAV controller on the ground, pilots on the ground, not airborne, so 178C generally does not apply, but 278 is. What are the differences? Well, we don't have time today, but you can look at our white papers for that. Now, unlike civil certification, the military authority generally has the right to access, receive, and audit all the artifacts. Militaries have a preference for their organizational project framework. That means SSR, System Spec Review, Critical Design Review, Preliminary Design Review, Test Readiness Review. Sometimes they add SOIs. We'll see the difference in just a moment, just before we sign out here in a couple minutes. And you can decide which is the best way to go, but they are not the same. And then finally, there's ongoing visibility into supplier problem reports and resolution. The militaries want a more hands-on approach to those problem reports. Remember, military projects traditionally have more dynamic requirements, meaning they're changing during the life of the project. As the military mission changes, the threat changes, the needs change. Now, as we promised, there's a difference between military and civil coordination meetings. Let's take a look at that. In blue on the top is military. In green on the bottom is the equivalent civil. Now the civil standards, 178, 254, 4754, they use the bottom, green. The military traditionally, 2167A, 498, 882, they use the top. But guess what, folks? They're not the same. The military doesn't want to change. So what could we do? I have seen projects, many of our dozens of Aviation engineers have seen projects where we do both. We don't like that, but the customer says, we're following 178, 254, 4754. Let's have both SOIs and military SSR, PDR, CDR. Goodness gracious. That is 9 meetings, 5 military meetings, plus 4 civil meetings for a total of 9. Don't we all love going to extra meetings and spending the money and time? Now, when we at Aviation have military projects, this is what we do. We reconcile the meetings. they're not exactly the same. For example, look, SSR traditionally comes before SOI1. PDR comes way before SOI2. Even CDR comes before SOI2. But consider, what is a preliminary design review? How preliminary is it? What is a critical design review? This is aviation. Everything's critical. Well, in civil, we say, you know, let's do an SOI2 when everything's complete, or we can prove that we're minimum 50% complete at a minimum. That's using 8110, 105, 49. So what we recommend doing is this: combining SSR, SOI1, having a separate PDR, and then combining CDR and SOI2. They're almost the same. TRR is right before SOI3, so let's just combine it. And then SOI4, our compliance review, our final review of stage of involvement, right before we do flight testing, certification, we can combine with the first article inspection or deliveries. A much more efficient. We have 5 meetings, not 9. They're not the same. Nice change for military. Does anyone care about cost? That's a joke. You all do. None of you have unlimited money or time. So what are the costs of military compliance? How much more does 178, 4754 applied to military cost? We'll see the answer in just a moment. Here's the breakdown. CM and QA is typically 10% of a project on a military project. The certification, DER, CVE, that's additional 2 to 3%. Now, DERs are not required, nor are ODAs, organizational approvals, on military projects. But if we don't have DERs or ODA, that's picked up by quality assurance. Now, management, we always need those folks in the nice suit and the nice tie. They got to manage the project. Management is 4 to 7% traditionally. Requirements development is really key. It's important, 10%. If we don't have model-based development, this is a standard structure decomposed development. Design comprises 10%. If we're using modeling per DO-254, then we'll see that much better, much higher, I mean. And then coding is 25%. Verification is about 1/3 of the entire budget. So on a military project, what are the top 6 cost drivers, things that you want to address to control those costs? Number 1, military DAL, okay? Considering the FHA, what is the criticality level, development assurance level? You need to answer that. And then what about the military mission equipment? What's their certification? What's their role in safety? What's the operational engagement rules for the pilot when we send waypoints for drops, missile launch, anti-submarine warfare? Are those commands to the pilot or merely suggestions? Then allocate the detailed requirements. Traditional military projects do not have the level of detailed requirements. We need to minimize assumptions. We need to show that most of the core code coverage, remember AFuzion's general rule of thumb. The rule of thumb says we should get 90% code coverage, logic coverage, by simply verifying, testing our requirements. So, accurate and thorough reviews, having detailed plans, a checklist that prove that the engineers didn't make assumptions, they did things according to the plans. Then minimizing the code and logic changes. These are really key to controlling the cost. Efficient testing. Military testing is typically done by very senior people with gray hair on the outside or the inside, and they have domain knowledge. They know what the system should do. However, there's a lot of manual testing on military projects. A far more efficient way is automating the test. The problem is, who receives the benefit of automation? It's the second project, the people repeating the test. Who pays for it? The first project, the people originating the test. Folks, your projects, especially on the military, they last for decades. So automate those tests. Make sure you have more automation and less overlap with your testing. There you have it, folks. You're done. 46 minutes from AFuzion, a small subset of our normal testing. Let's see how we did on your quiz. Look at that. All of the answers are false. Number one, traditional legacy military system standards emphasize safety? No, no. They emphasize domain knowledge, system, black box. But now they need to emphasize safety with 4754, 4761. A legacy similarity, number two, between military and civil aviation was white box testing, where we open the box. We look at the design and code. Oh no, that wasn't done on testing. We had informal unit testing, but now we do. Number three, guidelines such as 4754A for systems and aircraft, 4761 for safety, are not commonly applied to military today. That's false. They are increasingly commonly applied. Again, for our projects, the majority are. Out in the other world, non-AFuzion projects, we think it's at least 70%. Someday, 90 or 95%. Number four, PDR-CDR, preliminary design review, critical design review, is almost identical to SOI 2. No, it's not. It's rather different, as we saw 5 minutes ago. And number five, applying 4754-61, 178C 254 to military projects should increase the cost by 150 to 200%? No. If you have a good compliance, good processes, CMMI level 3, for example, which all of you should have, that's rather the minimum, we think the cost is 25 to 40% greater. If you want detailed justification for that, we have two white papers, the military compliance white paper and DO-178-254 costs versus benefits. Justifies that, and as we can show it, much, much less than that. But we do see a lot of projects with that. Well, there you have it, folks. You are done. Looks like we have a lot of questions. I'm not sure we're going to get to them all. The ones that we don't get to, let's go ahead and invite you to submit those by, well, you know what, never mind. We'll just get to them by doing an email exchange with you in private. I'd like to turn it over to Mr. Jeff Stevenson, who manages our business operation, coordinates with all of our clients. And if you have detailed questions later, it's Jeff you want to contact. Jeff, are you on board?
Yeah, sure am. Hi, everybody.
Awesome, awesome. Do you want to give a quick overview, or do you want to just go dive right into your questions, Jeff, the ones that looks like the attendees have asked?
Yeah, we'll start with a couple questions. The first question I see is, does a military avionics certification apply to UAVs?
Oh, that's a great question. You know, traditionally in the past, it truly did not. The UAVs starting, I guess we're probably under non-disclosure agreement with 5 or 6 of our clients that build UAVs, but those UAVs, legacy UAVs, were originally built in the late 90s, 15 years ago, and they were built for very specific missions that the US and other militaries were engaged in. They simply didn't have time to add the extra 25–40% schedule cost. It wasn't so much the matter of money, but those systems needed to be deployed. So the legacy systems did not follow 178. They used military standards on a good day, meaning rather light. It was all about getting them out the door and getting done and putting them in the field and using them for their job. Well, that changed because as those companies wanted to export, as they flew over civilian areas, all of a sudden the need for safety became more important. So unfortunately, going back and reverse engineering those UAVs is not so easy. Think of an old building, a couple hundred years old, and the building that I'm broadcasting, and if you can see behind me right now, our Fusion offices, this is an old building in Los Angeles. Imagine adding fire equipment, upgraded plumbing, electrical after the building's built. It's not cheap. It's not easy. It takes a lot of cost. It's the same as going back, white box, opening up those UAVs and adding compliance. So unfortunately, that's what they're doing. All the major companies have gone back, and we've done a lot of those projects for them, reverse engineered. Remember, there's 13 operating systems that were used in DO-178, and the majority of those, all but 3, were developed not using 178 from the beginning. They were reverse engineered. So today, the UAVs do require 178 and 254. Increasingly, they require the 4754. We see just starting the 4761 of the safety on the UAVs. So great question.
Okay, great. And so we've got another one here. It says the question is, does a military avionics certification use different plans, standards, and checklist templates?
Oh, good question. So they should not. Now, we see most military projects, again, were black box, very good system level domain, and they had higher level plans, probably 1/2 the size and detail as what's required under 178, 254, 4754, very lacking on the safety side. In theory, they could and should use the same plans, standards, checklists. We'd see a little bit of customization when customers acquire Aviation's plans, templates, checklists, hardware, software systems. We add a little bit of customization for mission equipment, for specific lessened safety assessment focusing on mission success probability, but a harsher environment for cybersecurity. Although we have that now too with the civil world, as we saw in one of our recent webinars, the application of DO-326 ED over in Europe 202 for cybersecurity is also being applied to civil aviation. So cyber is really important on mission. Imagine someone hijacking your UAV, not a good thing. So we really need to be able to enforce the cyber. So generally the checklists and templates are about 95% the same. Aviation customizes ours for our clients, and many dozens of companies use our Aviation checklists. If you want a free sample, ask Jeff for one of those, or what it takes to acquire those from us, but they're pretty similar. Jeff, I think we're running out of time. I've got to run along to another client telecom audit that I'm doing in a couple of minutes. And I think we're about out of time anyway. Anything you want to add, Jeff?
Well, yeah, certainly. I mean, some of the services we provide are, in fact, a gap analysis, which is frequently needed for the military compliance. And, we also have resources available to assist companies that we do all the time with the development, testing, and proper documentation of all these things. So, we do more than just train. So if you have any questions, you can just reach out and we'll see what we can do to help.
Fantastic, Jeff. And there's our website. There's our email address, info@afuzion.com. And one of those people, we always reply back within 2 days max. So everyone, thanks again. Please apologize to your colleagues, co-workers who were not able to log in. We only have a limit of 1,000 people on these webinars, so we apologize, but we'll send out the recording link to everyone who registered, okay, even if they were not able to log in. So until then, folks, safe skies from Aviation. Thanks, Jeff, and safe flying, everyone. Bye-bye now.
Yep, see everybody later.